Optimal control theory, also known as dynamic programming. This is from Hoy's book in chapter 25 in the second, or if you have access to the third edition, you'll find it in the third edition. Now, what is optimal control theory? It is a theory used to solve dynamic optimization problems. Now let's see what a dynamic optimization problem is. So consider the following. A company's output depends on the amount of capital employed. So Q, which is output, capital Q is equal to small q of K, K is capital. We can form the profit function pi of K equals to P times QK, which is total revenue, P is the price, minus RK, which is total cost, since you're only using capital, this is the only cost. R is the rental rate of capital. Now, in order to maximize profit, we have the following first order condition. So if you differentiate this expression, you get P times Q prime K minus R is equal to 0. Now, this is a static condition, right? It looks at current profits only, right? And this is the sort of static condition which we have encountered in our studies of economics, right? In microeconomics, in mathematical methods for economics, whenever we encounter a profit function or a utility function, right, or a cost function, we maximize or minimize it, and we obtain a first order condition in which we differentiate it and set it equal to 0. So this is a static condition. Now, instead of looking at current profits, we may adopt a longer term view. So we could maximize the discounted sum of profits over an interval of time running from the present, t equals to 0, to a given time horizon, capital T, which is given by the functional j of k of t. Thus, we have this functional, which we want to maximize, and that is equal to the integral from 0 to capital T of e to the power minus rho t times pi, which is a function of k of t, dt. Now, this is just the continuous time counterpart of a discounting problem. E is the natural number, it is a constant. When E is raised to the negative power, right, you are effectively dividing pi with E, just as we do in a discounting problem. We divide something by a number. And rho is the discount rate, right? It is known, maybe it is 3% or 4% or 5%. And t is time. So e to the power minus rho t is a number with which we divide, or in this case, since we're multiplying it, we are actually dividing pi by e to the power rho t. Okay, so, and then we sum it over time 0 to capital T. So this is our discounted sum of profits. A function maps a single value for a variable like capital K onto a single number, while a functional maps a function like k of t onto a single number. So that's the difference between a function and a functional. And what is the difference between a static and a dynamic optimization problem? In a dynamic optimization problem, we choose a path of k, values, right? Values of capital, or a function of time, k of t, to maximize the functional j. While in a static problem, we choose a single value of k to maximize a function like pi of k, the profit function, right? We would choose a single value of k to maximize this entity. Now suppose the stock of capital changes according to k dot is equal to I of t minus delta k of t. Let capital C of IT be the cost of purchasing IT of capital at time t. Then profits at time t are pi, k of t I of t is equal to P times Q, which is total revenue, minus cost. We now have a dynamic problem. Current investment affects current profit as it is a current expense. It also affects future profits since it affects the amount of capital available for future production. The firm's problem can now be written as, you want to maximize this functional, which is equal to the integral from time t is equal to 0 to capital T of e to the power minus rho t times pi, right? So this is the discounted sum. Subject to these two conditions, there's a differential equation governing k dot is equal to it minus delta kt. And there's an initial condition, k of 0 is equal to sum k naught, right? So capital at time 0 is equal to sum k naught. Usually this is positive. The firm has to choose a path for I of t, or investment. Once that is chosen, then the path of k of t is determined completely. Now here's the question. What is the path of k of t? And the answer is that there are several possible paths. One possible path is I of t is just equal to delta k naught, which is a constant amount of capital over time. K naught is a constant, delta is a constant. So you have a constant amount of capital over time. Or I of t could be 0, which implies that there is no investment. That is also a feasible path. If you choose not to invest, then I of t will be 0. Or I of t is equal to a e to the power alpha t, which is an investment path starting with I of 0 is equal to a. So when t is equal to 0, you have a into e to the power 0, or a into 1, which is a, right? So I of 0 is equal to a. And then it increases over time at the rate of alpha, if alpha is greater than 0, or it decreases over time at the rate of alpha if alpha is less than 0. Indeed, any function of t is a feasible path. We choose the path that maximizes the functional j of it. Such a path is found out by using optimal control theory. Now, this is a diagram which shows an investment path defined by I of t is equal to a, e to the power alpha t. Here, alpha is less than 0 or negative. And so the time path tells us that at time t is equal to 0, you start off at I naught. And then as time progresses, as t becomes bigger and bigger, your investment falls, right, at the rate of alpha. And here, of course, alpha is negative, until it sort of reaches an asymptotic value of delta k star, which is a constant.